Hi students, myself Vedamurthy. You are watching Chemistry Class 11, Unit 4 and Part 5, Chemical Bonding and Molecular Structure. Today in this video we are going to discuss about hybridization. Pauling introduced the concept of hybridization to explain the characteristics of the geometrical shapes of polyatomic molecules, for example methane, ammonia and water, etc. The atomic orbitals combine to form a new set of equivalent orbitals known as hybrid orbitals. The hybrid orbitals are used in bond formation unlike pure orbitals. The phenomenon is known as hybridization, which can be defined as the process of intermixing of orbitals of slightly different energies so as to redistribute their energies, resulting in the formation of new set of orbitals of the equivalent energies and shape. Say for example, when 1 2s and 3 2p orbitals of the carbon hybridized, so there is the formation of the four new sp3 hybrid orbitals. So what are the salient features of the hybridizations? The main feature of the hybridization, the number of hybrid orbital is equal to the number of atomic orbitals that get hybridized. Secondly, the orbitals or hybridized orbitals are always equivalent in energy and shape. Third one, the hybrid orbitals are more effective in forming stable bonds than the pure atomic orbitals. And the fourth one, so these hybrid orbitals are directed in space in some preferred direction to have a minimum repulsion between the extra pairs, and thus a stable arrangement can happen. So therefore the type of hybridization indicates the geometry of the molecules. And what are its important conditions to make the product is hybridization? See, the orbitals present in the valence shell of the atom are hybridized. The second condition is the orbitals undergoing hybridization should have almost equal energies. Third one is the promotion of the electrons is not essential condition prior to the hybridization. And the fourth one is it is not at all necessary that only half-filled orbitals participate in hybridization. So in some cases, even filled orbitals of valence shell can take part in hybridization. So now we'll discuss what are the types of hybridization. So there are various types of hybridizations involving in sp and d orbitals. So different types of hybridizations are as sp hybridization, sp2 hybridization and sp3 hybridization. Now we'll go in detail what are sp hybridization and its examples. See, sp hybridization is a type of hybridization which involves in the mixing of 1s and 1p orbitals, resulting in the formation of the two equivalent sp hybrid orbitals. Here s and pz orbitals are suitable for sp hybridization if the hybrid orbitals are lie along the z-axis. If the hybrid orbital lie along the z-axis, each sp hybrid orbital has 50% s character and 50% p character. Such a molecule in which the central atom is sp hybridized and linked directly to the other two central atoms possesses linear geometry. So this type of hybridization is also known as diagonal hybridization. So you can see in the picture here, you can see the picture here, the hybridization. The two sp hybrid point in the opposite direction along the z-axis, okay, along the z-axis. So each sp hybrid orbitals along the z-axis, in which which is directly linked to the two other central atoms, possesses a linear geometry. So this type of hybridization is also known as diagonal hybridization. The two sp hybrids points in the opposite direction along the z-axis with projecting positive lobes and very small negative lobes, which provides more effective overlapping. So which resulting in the formation of the stronger bonds. For example, in barium chloride, the ground state electronic configuration of barium is 1s2 2s2. Okay, whereas in the exit state, one of the 2s electron is promoted to valence of the 2p orbital, so to account for its bivalency, that is 1s1 2s 2s2. Okay, here, so the one 2s and one 2p orbitals gets hybridized to forms two sp hybrid orbitals. So these two sp hybrid orbitals are oriented in opposite direction, forming an angle of 180 degree, 180 degree. So this is one. Okay, here each of the sp hybrid orbitals overlaps with the 2p orbital of the chlorine axially, and for 2be-cl sigma bonds are forming. Be-cl sigma bonds, these are sigma bonds. Okay, so this is about sp hybridization. Now sp2 hybridization. In this type of hybridization, there is involvement of 1s and 2p orbitals. 1s in sp2 hybridization, 1s and 2p orbitals are involving to make the hybridization. So here we'll take the one example, boron trichloride. In boron trichloride, the ground state electronic configuration of the central boron atom is 1s2 2s2 2p1. Okay, in the excited state, one of the 2s electron is promoted to vacant 2p orbitals, it becomes 2p2. Okay, so as a result, boron has three unpaired electrons. So these three orbitals, one is, what are those? One is 1s orbital and another is 2p orbitals. These three orbitals hybridize to form 3sp2 hybridization. So 3sp2 hybridization or hybrid orbitals. The three hybrid orbitals so formed are oriented in a trigonal planar This is the way. Okay, so in the trigonal planar, the arrangement and overlaps with 2p orbitals of chlorine to form B-Cl bonds. So therefore, in barium chloride, the geometry is trigonal. Okay, so the which bond angle becomes 120 degree. Okay, so now sp3 hybridization. In sp3 hybridization, by taking an example, we can explain methane molecule, in which there is a mixing of 1s orbital and 3p orbitals. 1s and 3p orbitals are forming sp3 hybridization. Okay, Yes. So the valence shell to form the four sp3 hybrid orbitals of the equivalent energies and shape. So there is 25% s character and 75% p character in each sp3 hybrid orbitals. The four sp3 hybrid orbitals including s, 1s and 2, 3 p orbitals formed are directed towards the four corners of the tetrahedron. Four corners of the tetrahedron. Okay. So the angle between sp3 hybrid orbital is 109.5 degree. 109.5 degree. So the structure of the ammonia and water molecules can also be explained with the help of this sp3 hybridization. In ammonia, the valence shell or outer electronic configuration of the nitrogen in the ground state is 2s2, 2p1x, 2p1y and 2p1z, having three unpaired electrons in the sp3 hybrid orbitals, and a lone pair of electrons is present in the fourth one. So these three hybrid orbitals overlap with 1s orbital of the hydrogen atom to form 3n-H sigma bonds. We know that the force of repulsion between the lone pair and a bond pair is more than the force of repulsion between the bond pair electrons or two bond pair electrons. The molecule thus gets distorted and the bond angle is reduced to 107 degree from 109.5 degree. So the geometry of such molecule will be pyramidal in shape. Okay. So in case of water molecule, the four oxygen atoms 1, 2s and 3 2p orbitals. In case of water molecule, here 1, 2s and 3 2p orbitals undergo sp3 hybridization, forming 4 sp3 hybrid orbitals. So out of which 2 contains 1 electron each and other 2 contain pair of electrons. So these 4 sp3 hybrid orbitals acquire a tetrahedral geometry with the 2 corners occupied by the hydrogen atoms while the other 2 by the lone pairs. So the bond angle in this case is reduced to 104.5 degree from 109.5 degree. So and the molecule thus acquires a V shape or angular geometry. Okay, this is the example, formation of water molecule. So some other examples of sp3 sp2 and sp3 sp hybridization. So one of the in ethane, for example sp3 hybridization in ethane, C2H6, both the carbon atoms in ethane assume sp3 hybrid state. One of the 4 sp3 hybrid orbitals of the carbon atom overlaps axially with the similar orbitals of the other atom to form sp3 sigma bonds, while the other 3 hybrid orbitals of each carbon atom are used in forming sp3 s sigma bonds with hydrogen atoms. So therefore in ethane, C bond length is 154 picometer and C-H bond length is 109 picometer. Okay. In sp3 hybridization in ethane, in the formation of ethane molecule, one of the sp2 hybrid orbitals of the carbon atom overlap axially with sp2 hybridized orbital of the another carbon atom to form C-C sigma bond. C-C sigma bond. C-C sigma bond. Okay. So while the other two sp2 hybrid orbitals of the each carbon atom used for making sp2 dash s sigma bonds with the two hydrogen atoms. So the unhybridized orbital of 2px or 2py of one carbon atom overlap sideways with the similar orbital of the other carbon atom to form weak pi bond which constitutes of two equal carbon two equal electron clouds distributed above and below the plane of the carbon and hydrogen atoms. So thus in ethane molecule, the carbon-carbon bond constitute of sp2 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 dash sp2 sigma bond and one pi bond between p orbitals, which are not used in the hybridization and are perpendicular to the plane of the molecule. The bond length is 134 picometer. The bond length is 134 picometer. So the C-H bond is sp2s sigma bond with the bond length 108 picometer, and the HCH bond angle is 117.6 degree, and another H-CC angle is becomes 121 degree. Here 121 degree. So this is the formation of the sigma and the pi bonds in ethene. And lastly, sp hybridization in ethane C2H2 ethane C2H2 ethane molecule. How the sp hybridization form? In the formation of ethane molecule, both carbon atoms undergo sp hybridization. Having the two unhybridized orbital, that is 2py and 2px. These two are unhybridized orbitals in ethane molecule. So in that, one sp hybrid orbital of the one carbon atom overlap axially with the sp hybrid orbital of the other carbon atom to form C-C bond. Like this. That is C-C bond is sigma bond. Okay. So while the other hybridized orbital of the each carbon atom overlap axially with the half-filled s orbital of hydrogen atom forming sigma bonds, each of the two unhybridized p orbitals of both carbon atom overlaps sideways to form the two pi bonds. Two pi bonds here. Two pi bonds of each. So between the carbon atoms, so the triple bond between the two carbon atom is made up of one sigma and two pi bonds. Okay, that is C2H2 formation. So now the hybridization of the elements which involving the d orbitals. The elements which present in the third period contains d orbitals in addition to s and p orbitals. The energy of the 3d level orbitals or 3d orbitals are comparable to the energy of the 3s and 3p orbitals. The energy of 3d orbitals are also comparable to those of 4s and 4p orbitals. As a consequence, the hybridization involving either 3s, 3p and 3d or 3d, 4s and 4p is possible. However, since the difference in energies of the 3p and 4s orbital is significant. So no hybridization involving 3p, 3d and 4s orbital. So the important hybridization schemes involving sp, d and hybridized orbitals are, we can summarize like this, is when the shape of the molecule is square planar, so hybridization will becomes dsp2, and atomic orbitals which are involving in hybridization is d and sp2. So 2 1d orbital, 1s orbital and 2p orbitals will forming square planar geometry, which is an examples of NiCN 4 times all to the power of 2 minus and PtCl4 all to the power of 2 minus. In the tetrahedral bipyramidal geometry, here hybridization will make sp3 dehybridization. Here 1s and p3 and 1d orbitals involving to form sp3 dehybridization. Examples for this sp3 hybridization are trigonal bipyramidal is pf3 and pcl5. pf5 and pcl5. In square pyramidal, which is having sp3 d2 hybridization, here also 1s p3 and d2 2d orbitals are involving to form square pyramidal in sp3 d2 hybridization. Example is brf5. The last octahedral is sp3 d2 hybridization or d2 sp3 hybridization. In sp3 d2 hybridization, 1s orbital, 3p orbitals and 2p orbitals are involving in, okay, so that is either we can reverse it. So examples are sf6, crf6 and conh3 6 times. So now how the sp3 hybridization forming in PCl5. The ground state and the excited state outer electronic configuration of phosphorus is when the atomic number 15 are represented as like this. Ground state 3s2, 3p3, 3d0. When it is excited state, so 1, 2s or 3s electron will shift it to 3d orbital, so giving 3s1, 3p3 and 3d1. So now phosphorus pentachloride will form sp3d hybridization when the chlorine molecules are added. So the chlorine molecules when we are adding, so 5 1s and 3p and 1d orbitals are available for making hybridization to yield a set of 5 sp3d hybrid orbitals, so which are directed towards the corners of the trigonal bipyramidal. So and also it's noted that all the bond angles in the trigonal bipyramid geometry are not equivalent. In PCl5, the 5 sp3d orbitals of the phosphorus overlap with the singly occupied p orbitals of the chlorine atoms to form 5 p-cl, p-cl sigma bonds. So these 3 p-cl bond lie in one plane and make an angle of the 120 degree. Make an angle of the 120 degree with each other. So these bonds are termed as equivalent bonds. The remaining 2 p-cl bonds, one lying above and other one below the equatorial plane, so make an angle of the 90 degree with the plane. So these bonds are called axial bonds. So as the axial bonds pairs suffer more repulsive interaction from the equatorial bond pair. So therefore axial bonds have been found to be slightly longer and hence slightly weaker than the equatorial bonds, which makes the PCl5 molecule more reactive. And the second one, the formation of SF6, so which is the formation of sp3d2 hybridization. In SF6, the central sulfur atom has the ground state outer electronic configuration is 3s2, 3p4 and 3d0. In the excited state, the available 5 orbitals of, that is 1s and 3p orbital and 2d are singly occupied by electrons. So these orbitals hybridize to form 6 new sp3d2 hybrid orbitals, which are projected towards the 6 corners of the regular tetraoctahedron in SF6. Sorry, regular octahedron in SF6. So these sp3d2 hybrid orbitals overlap with the singly occupied orbitals of the fluorine atom to form s dash f S dash of sigma bonds. Thus, SF6 molecule has a regular octahedron geometry. Okay, so that is you can see in this picture. I hope this video you understood about this topic, hybridization. Thanks for watching the video.